Hi, I'm Dr. Jonathan Wilkes, a Research Fellow at the Future Biomanufacturing Research Hub. At Future BRH, we are using innovative technologies to advance sustainable industrial biotechnology. Many chemicals and materials that we use in our day-to-day lives are manufactured in processes that are not sustainable. These materials are often produced in energy-intensive processes that are dependent on fossil fuels, rare metal catalysts, and produce huge quantities of greenhouse gas emissions. But there is another way. Nature is a master of chemicals production, demonstrating incredible variety from the antibiotics that we use to treat infection to the scents that plants use to attract pollinators. All these chemicals produced by nature are formed through a series of chemical reactions called metabolic pathways. These pathways utilize a series of enzymes which can convert a renewable feedstock like CO2 or simple sugars such as glucose into chemicals that a living organism requires. Nature is then able to transform these chemical building blocks into diverse materials with remarkable properties. At the Future Biomanufacturing Research Hub, we are using synthetic biology and biotechnology to exploit nature's toolkit and develop bacteria and yeasts that can produce the chemicals and materials that we require. By feeding these microbes renewable feedstocks or waste products, we hope to create chemical production processes that are more environmentally friendly and sustainable than current fossil fuel-based technologies. To achieve this goal, we first identify enzymes found in nature that are capable of making a target chemical. If no enzyme can be found, it is necessary to engineer novel enzymatic activity using similar or related enzymes. More information on this step can be found in our video and technology platforms for enzyme engineering. Following the identification of suitable enzymes, the genetic information encoding a pathway is introduced into a microbial host. We are then able to test the production of the target chemical by feeding the microorganisms on sugar, CO2, or other waste streams. At this stage, it is unlikely that the quantities of the target chemical are high enough to be useful. To improve the production of the target compound, we use our synthetic biology knowledge and robotics platforms to facilitate the improvement of microbial strains in an iterative, high-throughput manner.
Hi, I'm Dr. Joe Webb, Research Fellow at the Future Biomanufacturing Research Hub. At this point, the conditions used for microbial growth and chemical production are suboptimal, so the best performing microbes from both the pathway and strain engineering pipelines are taken forward for the optimization of fermentation conditions. By performing multiple, small-scale fermentations in parallel, using automated systems to monitor and control conditions such as the pH, temperature and levels of dissolved oxygen, we can rapidly optimize the fermentation parameters required as we begin the scale-up process. Scale-up involves repeating fermentations and further tweaking of conditions in progressively larger reactors. When we are happy with the fermentation conditions and the target chemical is produced at a level that could be commercially viable, we will work with our partners at CPI and iBioIC to scale the fermentation process to industrial volumes. Approaching fermentation optimization in this way allows us to minimize the number of runs we perform, improve efficiency and reduce the resources required to bring a molecule to market. In the future, the goal is to expand on the approach taken in the Future Biomanufacturing Research Hub to disrupt the UK's chemical manufacturing sector and establish sustainable production routes to help realise the UK's target of net zero emissions. This is just one of the projects that we are working on as part of the Future Biomanufacturing Research Hub team. To hear more, just get in touch through the website.